Implement the find method, which returns whether an element is in the set, and if not, adds it as a new leaf if the argument add is true. Here's the skeleton code, and let's see what's immediately obvious. We're going to be using I as an indexing variable, which is pretty typical, and we have a while loop, and inside that, we'll be returning true. So based on the description of our function, it's here that we'll be figuring out if v is in the tree. This add part, well, that's if we're going to be adding our value to our tree. Notice that we aren't going to be getting to this if our value is already in our tree, because we'll have returned true. And if we're adding, well then v definitely wasn't in the list before, and so we'll need to return false. Then it makes sense that no matter if we add or not, if we don't return true, then we'll return false. Now let's look at the while loop. Because in this loop we might return true, this should clue you into the fact that we'll be looking at our list of items. So how can we use a while loop to iterate over a list? This is where the question really starts to test your data abstraction abilities. If this was a for loop, then iterating over the list would be trivial. But iterating over a list with a while loop is really, really hard. But don't let something like that distract you. Remember that our list is analogous to a binary tree. And trees are pretty different to lists, because you can't do a for loop over all nodes of a tree, but you can use a while loop. Then we should be asking ourselves, under what circumstances are we going to be in this while loop? The answer is so obvious that it's actually really easy to miss on your first time. We'll be in the while loop while we're in a non-empty tree. So when are we in a non-empty tree? Well, there's a clue in the grow function. It says that if I is greater than or equal to the length of s, or si is none, then we'll be in an empty tree. So this while condition would have to be the exact opposite of that. So while I is less than the length of our list, and that index is not none, we'll be in the while loop, and in the tree. So when do we return true? We could put if v is in self.items, and there's nothing really wrong with that, but that ignores the iterative nature that this code is going for. Also notice that in the add part, we're going to need to use I again, and it's only in this while loop that we can alter I. If we did put v in self.items, we might not mutate I appropriately. So this if statement is going to treat our list as an iterative/recursive object, and instead we'll put if self.items I equals our value. Now from our understanding of lists, you should see that this I equals statement is stating if we're going to either the left branch of the tree or the right branch of the tree. We know that the left branch is at index 2i plus 1, and the right branch is at index 2i plus 2. What you should notice is that either way, we're adding 1, so let's write that. The question then is if we're adding another one or not, and here the hint comes into play. We know from our understanding of binary search trees that the left node is always going to be less than its parent node, and the right node is always going to be greater. So if the value we pass in is greater than the current root, then we're going to be moving to the right node, which means that if our value is greater than self.items of I, we'll be adding 1. Otherwise, we'll be adding 0. And we code this with the line int v greater than self.items I. This is effectively the same thing as searching through the tree. And the single most important thing to note is that this is going to be the index at which our value either is or will be. Now we're at the adding part. Here it should be clear that we're inserting at our index, and the only thing we can insert is our value. So let's put that. But this raises a problem. This index might not exist in our list, so we need to fix it somehow. That's where the above line comes in. We might need to make our list bigger by some amount, and we can do that by adding another list. We need to think about what this list contains so that we'll still end up with a valid binary tree. We can't put any numbers here because that might make our tree invalid. Instead, we'll extend the list by putting in none. This will add space in our list without putting in any explicit data. We also know that we'll need to extend the list by some amount of nones such that our line down here works. So, we can multiply our list none by some integer to get a long list where every element is none, and now we need to figure out what that integer is going to look like. We know that we need to extend it by some amount such that its length is at most I minus 1. We could extend it by a list of length I, but then our resulting list would be I plus the length of our original list. So let's just subtract I. But now our list might not be adding anything. If we're adding d to this, we want a third index. But subtracting our index from the length of the list will give us 0, so we aren't going to be extending our list. You'll find that adding 1 is going to solve this problem, and now we're done. This last line is by far the hardest part of the question. My general advice is as long as you know what a line is supposed to do, if the implementation is tricky, try and answer the rest of the question instead. It won't do you any good to keep yourself stuck on a hard part of a question when there are potentially easier points in the rest.